Okay, today we're going to talk a little bit about lipids, but before we get into lipids, which are fat molecules and steroids, then I wanted to remind you about fatty acids, which you should have seen back in your carboxylic acid chapter. So if you recall, fatty acids have a carboxylic acid chain, or carboxylic acid on one end of a long chain of hydrocarbons there. So the carboxylic acid side is hydrophilic, right? Because we have some polar bonds here. So this is hydrophilic, which means water loving. And because of all the non-polar bonds between carbon and carbon and hydrogen, in the kind of tail side of things, we have a hydrophobic side. Water fearing. So we have one end that's polar, right? That's why it's water loving. And if you remember back to your introductory chemistry, that like dissolves like, so polar ends of molecules are more soluble in water, and hydrophobic or water fearing because it's non-polar. And we care about the way that these things interact with water because, again, our bodies are basically just a bag of water. We're walking bags of water with anxiety is one of my favorite memes that's out there. So how these molecules interact with our bodies is going to be dependent on the structures that's within them. So these are our fatty acids. In general, in the chain here, we have an even number of carbons. So this one in particular, because I ran out of room on the page, only has 6 attached to your carboxylic acid. And fatty acids are a primary component of lipids, or fats in general, and we'll kind of talk about the chemistry of that, but I just wanted to talk first about fatty acids and kind of remind you about what they do, and then we'll get into the structure of fats in probably a different video even. So let's just focus on fatty acids for now. Now, the reason that lipids have fatty characteristic, or that anything has fat or oil kind of characteristics, come from this hydrophobic tail. So the reason that anything is fatty or oily, and you can kind of picture that with anything in your diet, all of these characteristics come from this long hydrocarbon chain. Okay. Now there's a way that we can kind of stylize these fatty acids, and it's easier to do than just drawing it out every single time. We can usually just kind of talk about one end as being a head. So here's my polar head of my fatty acid molecule, and then if I draw my tetrahedrally coordinated carbons, I'm doing a longer chain now that I don't have to put all my hydrogens in there. Then this is my polar, you can call it the head of the molecule. And this is my non-polar or hydrophobic tail. Okay, so this is kind of a stylized version. And it's easier to use the stylized version for obvious reasons, but the polar part refers to the carboxylic acid end, and then the non-polar, of course, is your hydrocarbon chain. So this is the way that this would look kind of without context, but because we're talking about them with relation to biological connotations, because we're talking biochemistry now, then we usually care about how they interact with our body. So remember, our body pH is roughly 7.4, right? So our pH is how acidic or basic our body is. And because it's roughly 7.4, that carboxylic acid, so that end of our fatty acid chain, tends to not be a carboxylic acid, but instead it forms the carboxylate ion. Okay, so at this pH, because of this pH, in the body it tends to have this ending. So instead of having our stylized head there, I'm just going to do kind of, here's our C double bonded to our O, our carbonyl group. And it has an oxygen here that's lost its hydrogen because of the because of our body pH, because of the environment. And there's now our head of our fatty acid, and then here's the chain. This is, of course, a carbon at each of our points with the surrounding hydrogen. So this would be the way that the molecule would occur in our body. Okay, now in our bodies, because we're just bags of water, the polar heads will want to interact with the aqueous environment in our body, and the nonpolar tails will want less to do with that. So the natural way that these things will orient themselves, again, if we're just calling this a polar head and a nonpolar tail, is the polar heads will want to be out into the aqueous environment, aqueous meaning water, right? And the nonpolar tails will all be at the center. And if they create this little space for themselves, then now they have a non-polar environment at the middle, so no water molecules allowed. And then outside we have these polar heads that can interact with the water molecules in our body. So here's our water. It's got a slight negative end and a slight positive end. Here's our water. Slight negative, slight positive. So these guys are all happy in their polar heads, and if we picture this in 3 dimensions, then this can be this little sphere. And this little sphere with the polar heads on the outside and the nonpolar tails on the inside is all called a micelle. Micelle. And this micelle, again, is arranged with the hydrophobic parts away from the water and the hydrophilic parts out in the aqueous environment. Okay. Now this structure is going to be very important for a couple different reasons, but this is the way that these fatty acid chains are going to orient themselves if they're in solution, any sort of aqueous solution, but then in particular in our bodies. Now there's a couple different fatty acid characteristics that are in common for lipids that are naturally occurring. So we'll talk a little bit about synthetic lipids versus natural lipids. When we talk about the different types of fats. But in natural lipids, there are some common traits of fatty acids. Okay. And the first is that the fatty acids are usually straight chain. So usually there's no branches in the chain. So we've talked about branched alkanes versus straight chain alkanes. And so the difference is important, but when we're just talking about fatty acids and lipids, then this is basically what we're talking about here, usually just the straight chains. The second part, the tail part, are usually about 10 to 20 carbons long. And remember, that's also an even number. The third thing that they all have in common is including, so the even number of carbons includes the carboxylic acid group, so that's an important piece to that. So hopefully includes carboxylic acid. So that was not the case in the fatty acid that I gave as just a general one at the beginning, right? It had 6 carbons on top of the carboxylic acid group, so we should have had one more in the end because we have an even number of carbons including the carboxylic acid group. The carbons can be either saturated or unsaturated, but they will only have single or double bonds, so you will never see triple bonds. So remember, a saturated hydrocarbon is one that has a carbon bonded to 4 things. or these double bonds. And we'll talk about these double bonds in a little more detail because the double bonds give a lot of character to the lipids. So again, all of these structures build up to make larger macromolecules, these larger biological molecules that have significance in our bodies. The fourth thing they all have in common, so for these fatty acid traits within our lipids, is that they don't have any other functional groups besides the carboxyl group. So these are the 4 traits, kind of 5 if you include the carboxylic acid group here, the even number of carbons as an individual trait, that are in naturally occurring lipids. Okay, so let's talk a little bit more about these double bonds, these unsaturated carbon chains. So remember with unsaturated bonds, so double bonds in particular, we can have cis-trans isomerism. Right? And cis means that the functional groups or whatever are going on the same side of the double bond, and trans means that they're going on opposite sides of the double bond. So whatever it is that we're talking about that's hanging off the end of these things, cis is Latin for the same, trans is Latin for opposite. Now in our bodies, and again talking about naturally occurring fatty acids, they're usually in the cis conformation. So if it's in the cis conformation, this is going to cause kind of a bend or a kink in the chain of hydrocarbons. Okay, so we usually talk about the kink in the chain there, and the kink in the chain is caused by this cis conformation. So if we're picturing our carbons here, and all of a sudden we have a double bond, the cis conformation means that these guys are going to come off in the same direction. And then if we have the rest of our chain there, then that causes the chain to overall bend, right? So this kink or this bend in the chain happens because of the cis conformation about a double bond. Okay. Now in terms of characteristics, what this kink or this bend does is it causes these molecules with these long fatty acid chains to not stack up very well. And this also is going to lower the melting point then. So if we can't stack these fatty acids in as even of rows, right? If we picture the single bonded version, we'd have a bunch of hydrocarbon chains like this, and then we have another one here, and we have this nice stacking pattern, and stack them well, right? And so if we can stack them well together, then they're gonna solidify, right? It's gonna take more to bust these guys apart, but because of the fatty acid chain bend here, due to the cis conformation of your bond, then you're gonna lower the melting point of these molecules. So this means that lipids or fats or oils that are less solid, right, or more of liquids at room temperature are going to have these kinds of bends in their chains, and we'll talk about why when we get into structure in a little bit more detail. Okay, so the implication here is that they're liquids at room temperature. Now, in general, and kind of regardless of the bends here, when we're talking about fatty acid chains, the longer the chain that you have, the higher the melting point. So if we have shorter chains and more bends, then that's going to have lower melting points. But the longer the chain, kind of all things being equal, the higher the melting point. So if we go back to our characteristics of fatty acids, then if we have a chain that's somewhere between 10 and 20 carbons, the ones that are closer to the 20 carbons in a chain are going to have a much higher melting point than the ones with a smaller chain, closer to the 10 carbon side. Okay? All right, so our bodies, in terms of just fatty acids, our bodies make all of the fatty acids that we need, so we can synthesize everything that we need except for two. And these two then are called essential fatty acids, and these are ones that we have to get from our diet. Okay, so you've probably heard of essential fatty acids before. There's two. There's linoleic acid and linolenic acid. So we'll start with linolenic acid. Linolenic acid is also called omega-3 fatty acid, which you might have heard of that. And the way that its structure is, and I'm going to put my carboxylic acid here again. So we have our C, and again, this isn't naturally occurring in our body, so I'm going to put it as the carboxylic acid and not the carboxylate ion. One way to show these fatty acid chains is by doing the number of carbons in parentheses like this. And you guys maybe talked about this before, maybe not. So you put them in parentheses, and then there's 6 of them. So there's 6 of these H2s. And then if we look at this here, we have CH2, CH double bonded to another CH. And there's 3 of these guys. And then, sorry, this is going to go down the page here. Then there's CH2, CH3. So my total number of carbons then for this guy is 1, 2, and then I have 3 times 3, so 1, 2, 11, and then 6 is 17, and then 18 in my carboxylic acid. So again, it's an even number including that carbon, so we have 18 total. The reason that it's called omega-3, omega usually means the end when we're talking about Greek, so omega, the Greek omega, right, looks like that. And so omega-3 fatty acids, the last double bonded carbon is 3 carbons from the end, right? So we have 1, 2, 3 carbons from the end is my last double bond, and that's how that omega-3 name comes about. And omega-3s are good for your heart. One of the places that we get them is fish oil. So if you've seen fish oil tablets, walnuts, they're in flax seed. So these are all places that we get them in our diet, and also eggs. So eggs and fish, walnut and flax seed, and all of these things are pretty heart healthy, and we take omega-3s when we're wanting to take care of our heart. Okay, and again, we have to get these from our diet, so it's important to know kind of where we're getting them from. So that's linolenic acid. The other one that I mentioned is linoleic acid. It's the other essential fatty acid. So linoleic acid is called omega-6 fatty acid, another one you've probably heard of. And now just with our pattern, so omega again is the end, so if we look at the terminal carbon or the last carbon in the chain and we look 6 from that last carbon, then we're going to find the very last double bond in the structure. So again, we usually talk about the carboxylic acid side as the head and the methyl end, so the CH3 end is at the tail or the very end or the terminal end. So the last double bond is 6 carbons from the methyl group that's at the end. So I'm going to draw this kind of stylized, and I'm going to give myself a little bit of a diagonal because it's a little bit long. So here's our carboxylic acid. I'm going to draw it in lightning bolt or backbone format. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have a double bond. It is cis, right? So there's 10, 11, 12, another double bond. Okay, 13, 14, 15, 16, 17, 18. So this is another one with 18 carbons. So here's my terminal end here. Here's 18, 17, 16, 15, 14, 13, 12, 9. I did it right. Haha, yes. Okay, so here's linoleic acid, or our omega-6 fatty acid, and if we're counting from the end here, we have 1, 2, 3, 4, 5, 6. Here's my last double bond in the structure. Here's my omega-6 fatty acid, and one of the places that we find this one is in nuts. Walnuts have the linolenic acid, but other nuts will have linoleic, and seeds, and veggie oils. It's a place that we can get linoleic acid, omega-6, okay, in our diet. And again, these are fatty acids that we don't make, so they're important for us to get in our diets. And these are good for your heart as well. All right, if you have any questions on these, let me know, and that's it for now.